All right, let's go ahead and get started here. So I just want to start off with this question because I thought you're definitely gonna have something like this. So is f prime of 2 positive or negative? Well, if I look at 2, f prime of 2, well, this function is definitely decreasing at 2. So f prime of 2 is definitely negative because the slope of the tangent line there is negative. Or if you prefer, the function is decreasing. They mean the same thing. Okay. What about f double prime of 2? Well, if you're being asked about the second derivative, you're being asked about the concavity. So at 2, the function is definitely concave up, right? We're opening upwards. So certainly f double prime of 2 is positive, right? And here, if we want to write some reasoning, f prime of 2 is negative because f is decreasing at 2. And here, f double prime is positive too because f is concave up at x equal to 2. Question?
Is another reason for number 2 could be tangent line or something like that?
Oh yeah, that is a way of that's the equivalent way of saying a function is concave up. Yeah, so that's a good point. Concave up, the tangent line is below the graph. Oh, I like that a lot. Is below the function. Concave down, tangent line is above the function. And might as well say it. You get an inflection point when the tangent line goes through the function. Think of y equals x cubed at the origin. Right, the tangent line at the origin is definitely the x-axis and it goes through the function. You have an inflection point at the origin. Another way you could say this, just to kind of say, is that at 2, the first derivative is increasing. So function is concave up if the second derivative is positive, or if the first derivative is increasing. If you want to think about that for a second, if you move, so whenever I say the words increasing or decreasing, what direction am I thinking about? Like from where to where? I know I'm not saying it very clearly. I always mean from left to right. Whenever you're talking about increasing or decreasing, we always talk about from left to right. So if I go a little bit to the left here, the derivative is very negative. And then as I move to this point here, the derivative is less negative, and then the derivative is less negative. So as we move from left to right, the derivative is getting less and less negative, meaning the derivative is increasing. And when something is increasing, its derivative is positive. So if the first derivative is increasing, the second derivative is positive. Cool. Let's look at the next one. So f prime of -1. So we're looking over here. The derivative there is definitely positive. We can see that the function is increasing at x equal to -1. And whatever way you want to slice it, we can also say that the second derivative is positive as well, because the function is concave up there, or the tangent line is below the graph, or the first derivative is increasing. All three of those ways are ways of saying the same thing, just using different words. So, let me write this down. You can say f is concave up, or f prime is increasing, or I'm not going to write it, but the tangent line is below the function. All three of those things have the same meaning. Cool. Questions about any of this example? Okay. So I certainly have things I can talk about, but I suppose I should go. Yeah. So yeah, question. Bless you. Sorry. What? Sure. Let me give you an example. So let's say I'm going to go back to the usual kind of, for example. Let's say my function is x cubed minus 6x squared. And I want to find the inflection points. So first derivative is 3x squared minus 12x. I'm not going to worry about setting that equal to 0. I'm just going to move on. Second derivative is 6x minus 12. I set that equal to 0, and I factor out a 6, I get x equal to 2. Is that an inflection point? Maybe. We don't know yet. We have to check. And the way we can check it's an inflection point is by looking at the sign chart for the second derivative. So if I, on the right side of 2, I pick a number like 3 and plug it into my second derivative, f double prime of 3 is going to be positive. So my second derivative is positive, my function is concave up. If I plug in something less than 2, like 0, 0 minus 2 is negative, 6 times the negative number is still negative. Second derivative being negative means my function is concave down. So since the concavity is changing on the left side of 2 to the right side of 2, do we have an inflection point at 2? Yes, for sure. Right. Well, I should say yes, because the concavity is changing and the function is defined and continuous and differentiable. Yeah.
When they ask for an inflection point, they want us to find the y point too.
Well, so here's what I would say. When you get asked about an inflection point, it's going to be in the context of having to graph the whole thing. So yes, they're going to ask for the y coordinate as well. So really, like if we were actually asked the real question here, the process I should have gone through is the following. First, I should have found any intercepts. I feel like that's something that she actually isn't asking you to do on like, actually, let me look at one of these practice tests real quick here, just to be sure. I mean, you should, regardless of if she's asking or not, but I feel like that's getting kind of, let me see. Symmetries, domain, asymptotes. Maybe. Yeah, I don't see, at least in this question, specifically asking you to find intercepts, but you should always, when you're graphing a function, find the x and y intercepts. So yeah, sorry. So we'll come back to this in a second. So intercepts here, I would set x equal to 0 to find y equal to f of 0, which is 0. I would set y equal to 0, and then I would find 0 equal to x cubed minus 6x squared, factor, and get x equal to 0 and x equal to 6. And then we find the first derivative stuff. So we take our first derivative, set it equal to 0, factor out an x, a 3x. We would get x equal to 0, x equal to 4. And then for the first derivative stuff, we would also do the number line, put our critical values in the correct order on the number line, smaller to the left, larger to the right. And then we see what's going on with the first derivative. So pick a number larger than 4, like 5, I get a positive number. 3 times 5 times 1, yeah, positive. So my function's increasing. And I pick a number between 0 and 4, like 2, and I get 3 times 2 times negative 2, which is a negative number. So my function is decreasing. And pick a number like negative 1, and a negative 3 times a negative 5 is a positive number. I don't care about the actual values. I just care about whether it's positive or negative. So here's what we can say. This function has a relative maximum at x equal to what? 0 or 4? 0, because it's increasing, decreasing. And then, yes, we should also find the y value. So the point is really going to be 0, comma f of 0, which we know that f of 0 is 0, so it's equal to 0. And we definitely have a relative minimum at the other point, x equal to 4. And so the point we're actually going to graph, and we are going to label when we graph it, is 4, comma f of 4. So we actually have to go back to the original function and plug in 4. And it's definitely worthwhile if you're plugging back into the original function to factor it. And it's much easier for me to calculate 4 squared times 4 minus 6 instead of 4 cubed minus 6 times 4 squared. 4 squared is 16, 4 minus 6 is negative 2, so f of 4 is negative 32. And then since the concavity, so second derivative stuff, took second derivative equal to 0. And then I found on the other side it was concave down and concave up. So at 2, we do have an inflection point. And the y value would be f of 2, which is going to be, let's see, if I plug in 2 here, I get 4 times -4, which is -16. So to have an inflection point, you have to have a place where the concavity changes, and the function has to be continuous there. There's actually a little bit more of a condition, but really continuity is probably enough. So then to get back to the reason we started this whole thing in the first place is if you graph this. So when you're graphing your function on your exam, which we have, you should be looking at the first derivative sign chart. Because the first derivative sign chart tells you what the thing looks like. It's going to be going up until you get to 0, and then down until you get to x equals 4, and then up after 4. That's the whole picture, and we're just going to draw it and then label some of the points. Now, we know we also should hit the point 0, 0, and the point 6, 0. And then, okay, so up until I get to x equals 0, I'm increasing. So I'm going to be increasing. Now, don't come at this too sharply, right? Don't do this. Don't be like, here's my point, and I'll be like that, and then have to like turn around. Like it looks weird, right? You want to come at it so it smooths out as you hit that maximum. So we're going to do this. Smooth out. We're going to, that's not the best I've ever drawn, whatever. And then from here until I get to 4, I'm going to be decreasing. Then I have to smooth out. And then after that, I'm going to increase like that. There's the point 4, 30, -32. And there's my point 2, -16. And what I was saying is that at that inflection point, where the concavity changes from concave down to concave up, the tangent line, if you've drawn it well, the tangent line goes through the function. It's not always above or always below. On one side it's above, on one side it's below. Notably, right, on the concave downside, the tangent line is above the function. And on the concave upside, the tangent line is below the function. As we typically know concavity to work like that. Not that we've talked about that in here, but apparently someone said it somewhere. So yes, it's a nice way of thinking about concavity. Questions about anything we said here? We can definitely look at some more graphing examples. This is just kind of a nice, easy one to start with, I would say. Okay, let's do another graphing example. Let's do one where we have some, where we have like all the things. Meaning, in addition to having intercepts, maxes and mins, the inflection points, we're also going to have some asymptotes. So yeah, and she does. Yeah, I should definitely look at her stuff to be here to be super clear. I just want to make sure I'm presenting the questions in the same sort of way that she is going to ask you all. Let me take one quick gander here. I don't love this. Okay, well, we'll deal with that. So, yeah, good one, sure. So let's say our function is, I would ask about, I would do that, or do that. Sorry, 1 second. I'm working it out in my head what I want. Yeah, that'll be fine. Okay, let's say we have, x squared minus 4 over x minus 1 squared. Classic. And we want to find all the things. And so symmetries. I don't usually think about symmetries when I'm graphing. This graph doesn't have any symmetries, actually, does it? No, I've said this, no. Because here's how I know it doesn't. Where's my only vertical asymptote? Show me on your fingers. Where is my only vertical asymptote? Good. Yeah, it's at 1. If you have a vertical asymptote at 1, you can't be symmetric around the y-axis because you would have to have a vertical asymptote at -1. And you can't have rotational symmetry about the origin because you don't have a vertical asymptote on the other side to rotate around. So that's kind of when you can say that. Really, you should check f of negative x is equal to negative x squared minus 4 over negative x minus 1 squared. And that is completely different. Right? It's not equal to the original function, and it's not equal to the negative of the original function. So it's not equal to f of x, and it's not equal to negative f of x. So no symmetries of note. Question? No. A function can be neither odd nor even. Most functions are neither odd nor even. So to be even, you're right, it has to be f of negative x has to equal f of x. To be odd, f of negative x has to equal negative f of x. So let me ask you a different question. If I picked a number and said it wasn't even, would it have to be odd? Think carefully, think a lot about what kind of numbers exist in the real world. Okay, I picked the number 2.7. Not odd or even. There's lots of things that are not odd and not even at the same time. So being not even doesn't mean you're automatically odd. It usually doesn't mean that. Okay, so I'm just going to go through all the questions that she is asking on this thing. Yeah. Right. So so here's what I would keep in my head. When someone says when someone says an even function, the even function I would like you all to think of is y equals x squared. Or maybe y equals x squared plus 1. Where you have, if you flipped it across the y-axis, it would still look exactly the same. Or the right side of it has a mirror image in the left side. They're like looking at each other like, oh, you're the same as me over here. And the odd function you should think of is y equals x cubed. It has rotational symmetry. If you take that graph and in fact, I drew it over here. Not the best I've ever drawn it, but if you take this graph and you rotate it 180 degrees around the origin, does it look the same? It does. It's odd. It has odd symmetry or rotational symmetry or symmetry about the origin. They're always the same thing. So those are the two functions you should think of if you're trying to remember what kind of symmetry an odd or an even function has. And so, well, we'll do another example later that does have symmetry just to kind of see how you can incorporate that when you're graphing. All right, let's continue. Sorry, I was trying to undo this so I can see what kinds of questions she's for sure going to ask, or what kinds of how she's going to parse this out so that we can just. So the next part here is domain. So when we're talking about domain, you should really be talking about what's not in the domain. So what's not in the domain here? You all already told me. Yeah, 1 is not in the domain. So, but you can't say, you really shouldn't say x not equal to 1. It's not going to be good enough. Instead, you have to use interval notation and say it's going to be everything but 1. There's my domain. Everything but 1. Okay. Wow, really? Yeah. This is not the order I would do things in, but okay. Vertical asymptotes. This is where, yeah, this is kind of funky. So she does this thing where she gives you the limit as x approaches something from the right of f of x equals the limit x approaches some, let's use the red pen here for my blank space here. From the right of the actual function written out, x squared minus 4 over x minus 1 squared. Okay, so here's a big hint, and then it's supposed to equal something. Yeah. So when you're finding the vertical asymptotes, this limit, whatever this limit is, should end up equaling one of two types of things. There's only two choices for what this limit is. What's one of the choices? Infinity. What's the other choice? Negative. Those are the only things a vertical asymptote limit should end up equaling. Because what you're saying is, as I get close to this vertical asymptote, the y values do this or do this. They go up to infinity or down to negative. So we already know that the answer is supposed to be one of those two things. We just have to figure out the right sign. So where's my vertical asymptote? I know I've asked you twice already. One more time. At 1. So that's what x is approaching. X is approaching 1. the vertical asymptote value. And if I actually plug in 1, what do I get on top? -3. And the bottom I get 0. And is my 0 on the bottom really a very small, slightly positive number or a very small, slightly negative number? Has to be positive because the whole thing's squared. So it's going to be a negative over a positive, which means it's going to be a negative infinity. Yes. So, sorry, so like I'm not sure what you're saying exactly. If we had them in the bottom,
Yeah.
you mean if the domain didn't have 2?
If it wasn't 1.
Sure. Yeah. X should be approaching whatever the vertical asymptote value is. So what I would do if I was doing this problem is I would say my vertical asymptote is X equals 1. And then I'd be like, oh, that 1 has to go. That's what we're approaching. Right. Now, the thing that I think is weird about this particular question here is, I don't like the way this is being written on her exam because this problem has 2 vertical asymptotes. But it looks like you're doing the one from the right and the one from the left for the same value. So I'm a little bit confused as what she's actually trying to get you to do here, to be honest. Yeah, I don't know so if it were me, I'd probably write more. So, and then the other side of this, she's also asking, right, the limit as X approaches 1, or she's giving you this, but then giving it to you from the left of f of X is the limit as X approaches of X squared minus 4 over X minus 1 squared. And if we approach 1 again, because 1 is still the same vertical asymptote we're talking about, but now from the left-hand side, well, the top is still negative, and the bottom is still positive because it's being squared at the end. So we still have a negative over a positive, which means we're still going down to negative infinity. So what this tells me is that when I graph things later, my vertical asymptote, both sides are going to be going down, 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 to negative infinity. That's what that tells me. Great. Horizontal asymptotes. So I would say the vertical asymptotes are usually really easy to spot. They're just going to be typically, if you have a rational function, where the denominator is equal to 0. The horizontal asymptotes, on the other hand, you might want to skip until the end, to be honest. Because usually, once you have the shape of the graph from the first derivative stuff, you can usually kind of figure out what your horizontal asymptotes are going to be. Now, this one is not hard to do, so I think we should do it anyway. But I just want to say in general, it's often perfect. I would usually skip the horizontal asymptotes. So my function is x squared minus 4, x minus 1 squared. So to find the horizontal asymptotes, we're just taking the limit, x goes to infinity, of my function. This one, I would have made a different choice if I thought about it a little bit more. But what's my horizontal asymptote going to be? On your fingers. Not your middle finger, please. It's the same. It is also 1, and it might be easier to see if you multiply out both the top already is, and the bottom. Now, I think, if you recall, if the degree on the top and the degree on the bottom are the same, horizontal asymptote is the quotient of those leading coefficients, which is going to equal 1 over 1. So if the degree on top and the degree on the bottom are the same, just take the coefficients of your highest powers in each part and take that fraction. Well, that's kind of it as far as the asymptotes go. Yeah. That is given, but really, when I say what's the horizontal asymptote of this function, I'm asking the question, how does this function behave as you go way, way, way out back? You're asking, as x is really, really large, what value the function is getting really, really close to. You could also, although she hasn't in this exam, but you could also ask for the limit as x goes to negative infinity. But for any rational function, they will always be the same. There are some funky functions where the limit to the horizontal asymptote to the right and the horizontal asymptote to the left are different, but rational functions never have that behavior. So if you have a polynomial over a polynomial, you can expect the limit to infinity to be the same as the limit as you go to negative. Nice. Okay, so we've done all the, well, no, so this is, yeah, just on this first page somewhere, I don't know, I would find my intercepts just because that's my usual first thing. So y-intercept, set x equal to 0, and you're going to get y equal to f of 0, which is 0 squared minus 4 over 0 minus 1 squared, which is negative 4 over positive 1, which is negative 4. X-intercepts, which there can be multiples of, set y equal to 0. So we're going to get 0 equal to x squared minus 4 over x minus 1 squared. And when you want a fraction to equal to 0, you want the top to be 0 and not the bottom. So really, we just want 0 equal to x squared minus 4, and that factors x minus 2 times x plus 2. So we really want x equal to 2 or x equal to negative 2. Those are my x-intercepts. So now for the first derivative stuff. So I will say, he's going to give you the first derivative. We can calculate it here, but there's no point in doing that. I should probably just throw it into Wolfram Alpha because I don't want to spend our time calculating that. You're not going to actually have to calculate it. Sure, Wolfram should know this one. I've seen it. I do not really know it, but whatever. Yeah, cool. One moment. Sorry, messed stuff up. Let's see here. So we've got x squared minus 4 divided by x minus 1 squared. Cool, looks good. Let's do it. Right on. Cool. So here's the derivative. Let's go to the next page here. So given that the derivative f prime of x is equal to 2x minus 8. No, I'm gonna make it a little bit more challenging. Negative 2x plus 8 over x minus 1 cubed. I think the first thing she has you do with this is throw things onto the sign chart. So there are two numbers that should go on this first derivative sign chart. One of them should be relatively obvious. One, or more generally, if you ever have a vertical asymptote or multiple vertical asymptotes, all of those asymptotes should end up on every subsequent sign chart. For the first derivative, second derivative, because they're always going to be a place where any derivative is undefined. So the function's undefined there in the first place, the derivative cannot be defined. So one's going to be one of the, I don't want to fill it in yet because I don't know if it's the bigger one or the smaller one. So I need to also find where this derivative is equal to 0. If I set this equal to 0, you can just set the top equal to 0, but if you really want to think about what you're doing, what I'm really kind of doing is I'm just going to multiply both sides by the denominator. So on the left-hand side, I get the numerator, which is negative 2x plus 8. And on the right-hand side, what's 0 times x minus 1 cubed? Right. And so then you're just solving the top. So 8 equals 2x, so x equals 4. So I'm going to get 1 here and 4 here. And if for me, I would do one small thing. I would rewrite my derivative with the negative 2 on top factored out. Because factoring your derivative as much as possible makes it easy to see whether your overall sign is positive or negative. So pick something bigger than 4. I always start on the right. You can start wherever you want. I like to start on the right. I don't know why, I just do. Pick 7. 7 minus 4 is positive, 7 minus 1 is positive, but then there's a negative 2 there. So it's a negative times a positive, which is negative overall. And then you can either keep plugging things in, or you could observe that 4 comes from this factor, which has an odd power, but the sign's going to change. And 1 comes from this factor, which has an odd power, so the sign's going to change. You can also plug in points. If I plug in 2, 2 minus 4 is negative, 2 minus 1 is positive, and a negative times a positive is a positive. And if I plug in 0, 0 minus 4 is negative, 0 minus 1 is negative, and the negative times a negative times a negative is a negative. I know I'm saying times even though I'm dividing, because division and multiplication have the same effect when you're just looking at the sign, right? A negative times a negative is the same as a negative divided by a negative. You still get a positive result either way. So you can think of division as multiplication. It really actually is, right? Multiplying by 1/2 is the same as dividing by 2. They're literally the same thing, just seen different ways. So then on your sign chart, you really should think about what the function, and she's done it. She's written for you F prime and F on your sign chart. So you'd be like, okay, my function is decreasing, increasing, decreasing. Okay, I'm going to ask you all a trick question. Where is my relative minimum? Don't fall for the trick. It's a trick. Right, so where's our relative minimum? There isn't one. There is no relative minimum. You can't have anything at a vertical asymptote. Vertical asymptote wins. You get nothing else. Yeah.
Let's say I do think that 1 is the local minimum,
Mm-hmm.
and then I try to find the y value.
Right.
That's how I
Well, right. Well, like if you try to find the y value, it's going to be undefined because you need
yeah,
division
so
by
then
0.
I'll know that.
Right, exactly. Yeah, that's another. Yeah. So yeah. So we have no local minimum. Also on this sign chart, what you might do is if you know something's a vertical asymptote, draw in the vertical asymptote. There's nothing that says you can't do that. So no local minimum. But we do have a local maximum at +4. So local maximum at x equal to 4 and y equal to f of 4. I really can't stress enough how much I would encourage you to just start by writing the y coordinate is f of whatever your x value was, and then go back and actually plug it in to the original function, right? Not to the derivative. If you plug it into the derivative, what are you going to get? If I plug in 4 here, I'm going to get 0. You can still get a y coordinate with 0, but most of the time you won't. So if you find yourself plugging in, you're getting 0, double check that you didn't accidentally plug it into the derivative. You should be plugging this into the function. So we're going to get f of 4. My function, where'd you go function? It was x squared minus 4 over x minus 1 squared. Yeah. So it's going to be 4 squared minus 4 over 4 minus 1 squared, which is 16 minus 4 over 3 squared, which is 12 over 9, which is 4/3. Great. Okay. And then I guess we should talk about this. So I will say most of the time you kind of have enough information at this point to draw most of the graph. But let's find the second derivative stuff. So let's go ahead and just throw in the second derivative here. I definitely don't want to calculate that second derivative. It's terrible. Sorry, 1 second. It's going to be, let's see, negative 2x plus 8 divided by x minus 1 cubed. Here's what you should expect to happen. The second derivative should have a denominator that's x minus 1 to the 4th. Every time you take another derivative, your power in the denominator just gets 1 larger. And it's 4x minus 22 over x minus 1 to the 4th. Oh yeah, I remember this. I've definitely given this example on an exam before when I used to teach in Colorado. And I'm sorry, that's the wrong thing, apologies. And I've lied about what the derivative was to make it easier for the students. I lied and said it was 4x minus 20, so that the critical point was a little easier to find. The moral of the story there is don't check these. They could be wrong. She doesn't want you to check them. It doesn't matter if they're wrong. Use whatever you're given. Okay, so now sign chart for my second derivative. And I want to point out, she's giving you a big clue on your sign chart. She is telling you how many critical points should go on your sign chart, at least on all these practice exams. Right? She's giving you the little circles. Use the clues you're given. So I know that 1 is one of them for sure. And the other one I'm going to get by setting the top equal to 0. So I'm going to get 4x equal to 22. X is going to be 22 fourths, which is 11 halves. And if you like a decimal, you can say it's 5.5. So there's x equals 1. There's x equal to 11 over 2. Now we do the same game we played before. Prime, sorry, F, double prime, and F. So pick a number bigger. Oh, I wrote the wrong thing here, though. I said fourth, but I wrote third. To the fourth power. So plugging something larger than 11 over 2, like 100. 400 minus 22 is positive. Anything to the fourth power is positive. So the whole thing is positive. Which means the function is concave. And then between 1 and 11 halves, let's pick 2. 8 minus 22 is negative. The bottom is positive. Negative overall. Concave down. And on the other side of 1, if we pick 0, 0 minus 22 is negative. Bottom's always positive, so it's again negative. Concave down. Do I have an inflection point? Where does it live? 11 over 2, 5.5, whatever you want to call it. So my inflection point is at x equal to 11 halves, and y is equal to f of 11 halves, which, yeah, is kind of gross. Sometimes which is why I shall probably try to give you something that's fairly nice. But yeah, we definitely want the x and y parts. I do not love the graph sheet giving you the graph on here. Yeah. Just the numbers are so big, like they seem like they're in the way of the graph you want to draw. But so f of 11 halves, if we plug that back into the original function, it's going to be 11 halves squared minus 4 over 11 halves minus 1 squared. And I would not simplify that. If it looks gross like that, do something else. If you really have all the time in the world at the end of your test, then you can go ahead and try and simplify that, but you really shouldn't. Someone asked Chelsea, can you solve for the numerator and the denominator separately? Do you have to multiply the denominator out when solving for the? When you say solve for the numerator and the denominator separately, do you mean setting them equal to 0? Yes. Well, yeah, if you're finding critical points, yeah, just remember that the 1 technically is not an actual critical point, although it doesn't really matter for this class. 1 is a critical point, and yeah, so yeah, I'm just not even thinking about setting the denominator equal to 0 because I think it's relatively straightforward to see that x equal to 1 is going to be a place where the derivative is undefined. And it should be because we know that whenever you have a vertical asymptote, every subsequent derivative is going to be undefined at that vertical. Or more generally, if a function is undefined at a point, all of its derivatives are also undefined at that point. True story. Yeah. So then finally, putting it all together, here's how we're going to put it all together. Here are the things you should do first. Plot your points and your asymptotes. So specifically my intercepts of asymptote. So my vertical asymptote was x equal to 1. I would label it. And my intercepts were, I forgot what they were. Let me go back and look. I think they were plus or minus 2. Yeah, plus or minus 2. So 2, negative 2. And I also had a y-intercept of negative 4. Often we make the y-axis a little bit like less in. The x-axis is usually wider, like the x values are more spread out from each other. Like the distance from 1 to 2 is more than it is on the x-axis than it is on the y-axis. So usually more y values there. And then I also have a horizontal asymptote of 1. You should definitely draw your asymptotes as dashed lines, unless they're on one of the axes. And then, so those are all the points I have. I also know, I have a couple more points. I know I have the relative maximum and the inflection point, but I don't want to really plot those yet. What I want to do is I want to use my first derivative sign chart. So take a look here. When you're graphing it, you should be looking at your first derivative sign chart and saying, okay, before I get to 1, the function is decreasing. After 1, the function is increasing. And then after 4, the function is decreasing. So I should think about what's happening at 4. So we said that the relative maximum was the point 4, 4/3. Is that going to be above or below my horizontal asymptote? Good question. Is 4/3 bigger than 1 or smaller than 1? Right. So 4, 4/3 is going to be somewhere above. Okay. So I'm just following the arrows. So starting from the left, we never cross the horizontal asymptote unless there is good reasons. There's no reason to cross it over here. So I'm just going to do this. Decreasing from left to right. And as you go further to the left, this just gets closer and closer to y equal to 1. Okay, from 1 to 4, I need to increase. So I'm going to start way down here. And then we're going to get close. We're going to go through that point and hit that max. Now, when you're going towards a maximum, just like we did before, you want to approach it with the thought that that's going to be the top. And so you need to kind of flatten out so that after that, you're going to be going down. There's my maximum, 4, 4/3. And then after that, we decrease. But now here's the thing. Let me just, right? You're not going to do like this. You're not going to decrease and just keep going down, 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 down. We can't for a number of reasons. We don't have any more x-intercepts to cross through. And we really shouldn't cross this horizontal asymptote unless there's a good reason to. Also, the function changes concavity, right? It's supposed to start being concave up. So what happens here is we kind of flatten out. And right there, that's my concavity point, my inflection point, sorry. 5.5, comma, whatever f of 5.5 is. I would actually label it that way unless I had gone back and found the value. That's the graph. Yeah. Yes, you can cross a horizontal asymptote, not a vertical, because a horizontal asymptote only says the function gets really, really close to 1 as you go way, way, way out to the right or way, way out to the left. It doesn't care at all what's happening in the middle of the function. All kinds of crazy stuff can happen. In fact, you can have functions that cross a horizontal asymptote an infinite number of times. Like sine of x over x. If you graph that and you go way out to the right, horizontal asymptote is 0, and the sine of x over x crosses it an infinite number of times. Kind of cool. Okay. Should we do another graph or should we do something else? Something else. Okay. What else should we do? Oh, we should do some optimization. Unless there's a question. Yeah. Uh-huh. Sure. Right. 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 Relative extrema. So relative max or min is when the first derivative is equal to 0. And then if you want to have a maximum, it's where the derivative goes from being positive to negative because your function is going from increasing to decreasing. So that's going to be a relative. So if we call this like our critical point, must be from C, then C comma f of C is a relative max. On the other hand, if on your sign chart at your critical point, the derivative goes from being negative to being positive. And when I say goes from, I always mean from which side to which side? Anybody? From which side to which side? Left to right, always left to right. You're always left to right. Always, always, always. So if we went from left to right, if you're increasing to decreasing or positive to negative for the derivative, relative max, if you go from decreasing to increasing or a negative derivative to a positive derivative, it's a relative minimum. But again, it's only true if the function is defined there, right? Just like in that previous example, we didn't have a relative minimum at the vertical asymptote, even though the function went from being decreasing to increasing. There's no relative minimum there because the function is not defined. And then yes, so just to confirm what you were saying, as far as inflection points go, it's exactly it's the same kind of deal, except for second derivatives. So for inflection points, you're finding where the second derivative is equal to 0, and then the concavity has to change from either positive to negative, or it doesn't matter which way it changes. So you can go from positive to negative, be concave up to concave down, or it can be negative to positive, concave down to concave. Either way. Again, the function has to be defined at that critical point to have an inflection point. You can certainly have, okay, here's a real quick example. Yeah. I'm not going to actually, yeah. Come on. Okay. So here's an example. The easiest example I can think of. F of x equals 1 over x. This function is always decreasing. Well, I should really say it's decreasing on the interval negative infinity to 0, union 0 to infinity. From 0 to, sorry, on the left side here, is it concave up or concave down? Concave down. How about over here? So my concavities chart, which, okay, fine, we can take some derivatives. The first derivative would be negative x to the negative second, which is negative 1 over x squared. So my first derivative is always negative, which makes sense because we just said the function was always decreasing. And my second derivative is positive 2 times x to the negative third, or 2 over x cubed. And if we plug in 0 to our second derivative sign chart here, we can for sure see that if x is larger than 0, my second derivative is positive, my function is concave up. And if x is less than 0, my second derivative is negative, so concave down. Do I have an inflection point at 0? Look at the graph. Is there an inflection point at 0? No. What do we have at 0? Vertical asymptote, which denies everything else. So no inflection point, even though the concavity changes, because the function isn't defined at 0. Cool. All right, let's do a couple optimization problems because I feel like that's something we haven't talked a lot about. There will definitely be an optimization problem on your exam. Optimization. How bad do you want to make it? Here. Yeah. Sorry, I'm trying to say. Let's look at what she's giving you. Ow. And my finger is still cut the other day. Let's make something up. Okay, here's something I could see her asking. Find the point on the graph y equal to, sorry, I have to think for a second. Sure. Square root of x plus 3. Yeah. Closest to the origin. This is a totally reasonable optimization question. How do I know it's optimization? Because I use the word closest. Right, I'm trying to find the thing that is either minimizing or maximizing something. So here's how I would start. I would start by drawing, actually, I really start by drawing a picture. Square root of x plus 3 looks like the usual square root graph, shifted 3 to the left. Here's how I know. What's the domain of this function? Well, domain. I'm going to set the insides to be, which means x is greater than or equal to, 3 left of where it would usually start, which is the origin. So here's my graph. Kind of exaggerated, but whatever. And there's some point, maybe it's right about there. I don't know what it is. When I don't know what a thing is, I give it a variable name. I'm going to call it x comma y. And I'm trying to find the point there so that the distance between that point and the origin is minimized. So I'm trying to minimize the distance, which is equal to, we have to know the distance formula, square root of x minus 0 squared plus y minus 0 squared. Unless she says she's going to give them to you, then yeah, because it could come. I mean, you don't have to. You just won't be able to do this question. Right? Like, so yeah, there's probably gonna be in your optimization problem some sort of geometric thing you need to know how to find the area or the volume, surface area of, or the distance between, unless she's going to give you the formula. I don't know. She might. I'm not sure what, not in her brain, right? Like, I don't know what she's thinking. So maybe she will.
Yeah, if we have time, can like make a list of.
Sure. I mean, sure. It won't be short though. Okay. So, nice thing about this though, well, actually, let's simplify this. Distance equals the square root of x squared plus y squared. It is always true that instead of minimizing the square root of x squared plus y squared or minimizing the distance, instead, a better choice that is equally valid, we're going to minimize the distance squared, which is just equal to x squared plus y squared. It is always, always, always an option to do this. It is almost always the better choice because it's less derivative, right? The derivative of this is going to be way less terrible than the derivative of that. But before I can take the derivative here, I don't know how to minimize a function of two variables. We need to write this as a function of one variable. You have to use your constraint. And the constraint is the limiting piece of information that maybe the two numbers add up to 100, or the volume of this box has to be 32 cubic feet, or in this case, that point is on the curve y equals the square root of x plus 3, which means we know that y equals the square root of x plus 3. So we're going to use the fact that y is equal to the square root of x plus 3. We're going to plug that in. So our new equation is going to be the distance squared is equal to x squared plus the square root of x minus 3 squared. And of course, we should simplify that. That's just going to be x squared plus x minus 3. And now, how do we minimize a thing? Always the same process. Right. Or more generally, you could say find the critical points. But yeah, I would agree. Set the derivative equal to 0. So the derivative here, so the derivative of d squared, you're just going to write d squared prime. Right, we're not doing anything fancy here. That's going to equal the derivative of x squared plus the derivative of x plus the derivative of 3. We're going to set that equal to 0. And then we're going to get 2x equal to -1, x equal to -1/2. We're not done yet, though. So after you've found your critical point, this is the time you should go back and read the question again and find out what they're actually asking for. So the question said, find the point. Did I find the point yet? No, I found half of the point. I found the x coordinate. Fortunately, finding the other half of the thing you're being asked to find, whether it's like the sides of a rectangle or the dimensions of a sphere or whatever, dimensions of a cylinder, usually you already have an equation to find that thing. I know what x is, and I have an equation that tells me what y is when I know what x is. So y is just going to equal the square root of -1/2 plus 3, which is the square root of 5/2. So my point is -1/2 comma the square root of 5/2. Alternatively, they could have said, instead of saying find the point, they could have said, how far away is the closest point? Meaning, what actually is that minimum distance? So then you would take your point and then plug it into the distance formula. So the distance, the minimum distance would have been the square root of x squared, which is -1/2 squared, plus the square root of 5 halves squared. Which feels silly to write, you should just write 5 halves. That's going to be the square root of 1/4 plus 5 halves, which is some ugly number that I don't really care about. 10/4, square root of 11/4. It's not really the point, but the point is that make sure you are really addressing what you're being asked to find. Sometimes it's the two things that give you a maximum or minimum. Sometimes it actually is the maximum or minimum value of the thing that you are maximizing or minimizing. I'm curious. Oh, I know what I was saying. I'm just, oh, we should do one of those two for sure. Yes. Just want to see. There's so many things. Okay, yeah, we got time. Yeah, okay, that's a good example. I don't think she wants you or is requiring you to check that the thing is giving you a maximum or minimum. So I wouldn't worry about that. Let's look at this one from one of her practice tests, which admittedly I think is a moderately challenging question. Manufacturer needs to make a cylindrical can. I'm just going to write down the details here. Cylindrical can that will hold 2 cubic feet of liquid. What dimensions will minimize the amount of material in its construction? Okay, amount of material is just code word for what? Amount of material used is just the surface area of the object. So here's my cylinder. I am thinking of like a Coke can. Not my best cylinder. Do we know any of the dimensions of the cylinder? Now, what are the usual dimensions that are like, what dimensions do we need to know everything about the cylinder? Well, we need to know how tall it is. And we need to know the radius of the circle. But we don't know either of them. All right, there are two things going on here. There's the thing we want to minimize in this case, and there's the thing that is the constraint. I always like to start with the thing I want to minimize, although people, I feel like most people want to start with the thing that's constraint. But okay, so we want to minimize surface area. Okay, the surface area is literally just the sum of all the areas. Cylinders are always challenging. What's the area of the bottom of the cylinder? Well, what shape is on the bottom of the circle? And the area of a circle is pi r squared. What's the area on the top of the can? So another pi r squared. Sometimes they will give you an open top cylinder, so you only have 1 pi r squared. Plus the around part. Here's how I think of the around part. I think of a roll of paper towels. And if I take off one paper towel that goes exactly all the way around, that paper towel looks like what kind of shape when you unroll it? Square, but it could be a rectangle, right? Maybe you got like one of the extra like long ones that like gives you like the select the size where like you get the half sheets and it's like 3 sheets long, so it's really more of a rectangle than a square. But the point is you get this rectangle, and the height of that rectangle is still the height, and the length of that rectangle is the circumference of the circle, which is 2 pi r. And so the area of this around part is 2 pi r. And that's what we want to minimize. Okay, we need, so but again, as is usual, the thing we're trying to minimize is a function of 1, 2 variables. So we need a constraint so that we can relate those variables and eliminate one of them in our equation. And our constraint is that the volume or the can needs to hold how much volume? 2 cubic feet. What's the volume equation of this thing? You're so close. You're thinking of a cone, and that's 1/3 pi r squared h. The cylinder just doesn't have the 1/3 part. More generally, when you have a shape that goes straight up and down like this, right? It's not like a weird cone kind of thing. It's always just the base area. The area with surface pi r squared times the height, which is h. Right? There's your base area. And you're just lengthening it out. Okay, and that needs to equal 2. Because someone told us it needed to. Because there's 2 different things. One equation is the thing we're trying to maximize or minimize, which is the surface area. That's how much area is on the top, the bottom, and all the sides. But then the constraint is talking about how much volume needs to be held. And the volume equation is pi r squared times h. And the way you can tell kind of the difference between them is any volume equation should have 3 dimensions multiplied together. R times h in this case. Any area equation should have 2 dimensions multiplied together. R times times h. Always true. Okay, so then we're going to use this to solve for one of these 2 variables and then plug in there. You can choose either one, but the better, easier choice should usually be very obvious. Do I want to plug in for R and solve for R, or do I want to plug in for H and solve for H? I want to solve for H because it's easier. I don't have to take any square roots. And I want to plug in for H because there's only one H to plug in for, whereas there's multiple places to plug in for R. So H is by far the superior choice here. So H is equal to 2 divided by pi r squared. And then we're going to plug that in with a 1H right there. So now my new surface area equation as a function of just R, I'm going to get rid of the H, going to be 2 pi r squared plus 2 pi r times 2 over pi r. Definitely in your interest to simplify this expression as much as possible before you differentiate and send it to 0. This is going to equal 2 pi r squared. And then here I can cancel a pi and an r to get 2 times 2, which is 4. And instead of doing 4 over r, I would recommend writing it as 4 times r to the negative first. That's going to be easier to differentiate. Okay, let's take the derivative. All right, it's going to be 2 pi times 2r is going to be 4 pi r minus 4r to the negative second, which is kind of disgusting. This is not a great problem because the numbers turn out kind of gross, to be honest. But if we set this equal to 0, here's how I would solve this. I would factor out, no, I don't know. I would do this. I would set 4 pi r equal to 4r to the negative second. I know this is not what I usually do. Usually I'm like factor. This is one exception when you've got negative powers. It's kind of easier and better to do it this way. And then rethink of this as 4 pi r equal to 4 over r squared. Multiply both sides by r squared to get 4 pi r cubed equal to 4, and divide both sides by 4 pi to get r cubed equal to 4 over 4 pi, which is just 1 over pi. So finally, r is going to equal the cube root of 1 over pi. Which I will admit is not the nicest problem. Are we done? What do we still have to find? H. But luckily, we have an equation for H right here. And all you should do at this point is just plug it in and not simplify. So I'm going to say, great, h is equal to 2 over pi times the cube root of 1 over pi squared. Don't do anything else unless you absolutely have to. Cool. All right, 245. What else should we do? There's like so many things. Talk about that, talk about that. I feel like we talked about anything. Is there anything specifically we should say? Oh, I know what I had a thing I want to make sure. So just so everyone, right, there's lots of derivative questions you're gonna have, but for sure one of them is gonna be something like find the derivative of f of x equal to, I don't know, tangent of x to the 3x squared power. And to do this sort of thing, really need to rewrite it as, I mean, you don't have to write it as y, you're using y, write it as y equal to this thing. When you have a function to a function, the way we always do this is the process of logarithmic differentiation. So what do I have to do first, or next, I guess? Right, take the natural log of both sides. And the reason we do that, so that then we can bring down the power on tangent of x. So this is going to get rewritten as the natural log of y equal to 3x squared times the natural log of tangent. And now we're finally in a position to differentiate both sides. The derivative of the natural log of some stuff is 1 over the stuff times the derivative of the stuff. On the right-hand side, I will always have to use the product. I'm going to get derivative of 3x squared is 6x times the natural log of tangent of x plus 3x squared times the derivative of the natural log of some stuff, 1 over the stuff times the derivative of the stuff. There's 2 more steps, but in my opinion, you can make it 1. We need to solve for y prime. So what do I have to do to both sides? Yeah, multiply by y. And then we have to replace y with what is equal. So I feel like you should really do it in one step and say y prime is equal to y, which is tangent of x to the 3x squared, times all of that. 6x times natural log of tangent of x plus 3x squared times secant squared x over tangent x. But you can take an additional step if you want to and say, oh, y prime equals y times all that, and then replace y with what. Yeah, I guess I'm curious here. One second, sorry. Let's see one thing. It's interesting. She totally gives you the volume equation of a cone. It doesn't give you any of the equations for the solid in this. Okay. Things you might have to know for optimization. Equations. Yeah, sure. Okay. Area stuff. Square. Area is x squared. Perimeter is 4x. Rectangle. Area is x times y. Perimeter is 2x plus 2y. Circle. Area is pi r squared. Circumference is 2 pi r. What other shapes? I guess triangle. Area is 1/2 a times b. And so perimeter is a plus b plus c, but more importantly, Pythagorean theorem, a squared plus b squared equals c squared. These are formulas that can come up really when you're doing an optimization problem or a, yeah, thank you. Very fun. These are more likely to come from related rates. I feel like related rates is more 2D stuff often. And then any other 2-dimensional shapes we can think of? I mean, there's lots of other two-dimensional shapes you can think of. Any other that are gonna come up? I don't think so. I don't think anyone's gonna be talking about a pentagon or a hexagon or an octagon or anything like that. Or a septagon or the deceptagon. Sorry. Transformer shape. Okay. So, and then we have volume stuff. Or 3D objects. Cube. Volume is x cubed. Why the third power is called the cube power, by the way. Surface area is x squared plus x squared 6 times. Right? But for any sort of rectangular prism, the surface area is just add up all the areas of the rectangle. There should be 6 rectangles in total. Find all the areas, add them all up. So for more generally, a rectangular prism or a rectangular parallelepiped, often called, and my picture is looking weird, but that's fine. The volume is x times y times z, and the surface area is, the front face is x times z, the side face here is y times z, and the top face here is x times y. But then every face I just mentioned also has an opposite face. There's a bottom face that is also x times y. There's a left face that is also y times z, and there's a back face that is also x times z. Which, if we draw in, right, the rest of it, maybe you see. There are 6 faces on a rectangular prism. And then there's really only 2 other ones I can think of. Oh, three. Cone. Can I draw a cone? Maybe. Cone that has a height of h and a radius of r. The volume is 1/3 pi r squared h. And no one should ever ask you about the surface area. Then the last 2 shapes that I can think of are the cylinder, which we just talked about. I will draw in this where the volume is pi r squared times the height, and the surface area was a little tricky. It was the area of the 2 circles, which is pi r squared times 2, and then the area of the round part, which was the circumference, 2 pi r times the height. Finally, the last shape you might be having to talk about is a sphere. And the volume of a sphere is 4/3 pi r cubed, and the surface area of a sphere is 4 pi r squared. Interesting fact. The area of a circle is pi r squared. What's the derivative of pi r squared? With respect to r. To what r? Okay, right. The volume is 4/3 pi r cubed. What's the derivative of 4/3 pi r cubed? Pretty neat. It's only true for circles and spheres, but it is an interesting fact. I am pretty sure it's something to do with the fact that a circle and a sphere give you the most area per perimeter or volume per surface area of any of the shapes we deal with. But yeah, kind of neat. That's an easy way to remember them, right? If you know one of them, you can find it by taking the derivative. Cool. Those are the shapes I could imagine coming up in the context of optimization or related rates. Yeah. I can't think of anything else off the top of my head. Okay. You're welcome. Last thing I'll say. He's told you what's going to be on the test. Right? It's not like she's going to do something different, right? All of our practice tests look like this. So understanding the geometric meaning of the first and second derivatives. First derivative is talking about the slope of the tangent line, or if you prefer, if the function's increasing or decreasing. but she's typically asking you about the sign of the first derivative. You're just supposed to say, is it positive or is it negative at this particular point, based on what the graph looks like. And similarly, for second derivatives, she's just asking you if it's concave up, we're supposed to say the second derivative is positive. Or like, scratch your name. Dylan? What? Daniel. I was like, I think it's my brother's name, but I'm not sure. Yes, Daniel. Like Daniel was saying, if it's concave up, if the tangent line is under the graph. It's concave down if the tangent line is above the graph. It's a great way of thinking of it. Especially because you're probably going to draw the tangent line anyway to see if it's going down or going up. Finding the limit of the sequence of a function. If you're taking the limit to infinity. Oh, something to remember here, I guess I should point out, just as a reminder, if you have got the limit as x goes to infinity of some number raised to the x power, if that number is larger than 1, say like 4/3, that limit's going to be what? Infinity. You've got a number bigger than 1 multiplied by itself repeatedly. On the other hand, if you've got a number that is smaller than 1, like 2/5 raised to the x, that limit's going to be 0. Because it's getting smaller. It's still positive, right? 2/5 times 2/5 times 2/5 times 2/5. Positive, positive, positive. But getting smaller and smaller every time you multiply it by a number less than 1.
Will we get both points? Just like,
I don't know. I honestly don't know. I don't know what her expectation is behind how you're supposed to say that limit is 0 other than just saying it's 0. I suppose if you wanted to know, I mean, you could write words. You could say because 2/5. I would actually write the absolute value is less than 1 because technically if it's too negative, it could still blow up. Because the absolute value of 2/5 is less than 1, and I don't know, like, and a number less than 1, right? Number less than 1 raised to a higher power gets small. Right? You could write words like that. I just don't know what she actually expects you to say about something like this, other than just saying it's 0. Finding derivatives using the definition of the derivative. And then there's going to be an f of x to the g of x kind of one, like we just did. And then a couple other ones that will make you use the chain rule with product rule. Definition. I'm curious here. I just want to see one thing. I still got 2 minutes. Yeah, and it is at a particular point. So it should be not too terrible. Just make sure you're calculating things correctly and safely. And you can do it in one of 2 ways, really. You can do it as the limit as x approaches a of f of x minus whatever f of a is. You actually have to plug in your a value, right? Like if x is approaching, if it's at 2, you have to plug in 2 for every a. But there you have to find f of 2, so you have to plug that 2 into your function to find the value there. Or you can do it as limit as h approaches 0 of f of a plus h minus f of a all over h. Either way is fine. Pick something and stick to it. Tangent line to the curve defined implicitly. Implicit differentiation, and then right after you do the implicit differentiation, what's the next thing you do? Plug in the point and then solve for y prime. Don't solve for y prime first, and then plug in after. Plug in the point first, then solve for y prime. Linearization is kind of gross, but not that bad. Just make sure your problems are always a little wonky, I feel like. Because he's usually giving you kind of off the wall values. Oh, that one's not too bad. Yeah. Exponential growth and decay, we talked about that. And then related rates, optimization, and then the giant graphing problem at the end. You know what's coming. Study for it. For those of you that have your final tomorrow, best of luck. For those of you that have your final on Thursday, I'll be seeing you next week. I'll be in drop-in tomorrow. So I'll be in drop-in every day, 11 to 1, 2 to 4. So if you want to come get some help, get some help. For those of you who have your final tomorrow, study today, get a good night's sleep, eat some breakfast, do the things you need to do to adequately prepare your body as well as your mind for your exam tomorrow. Sleep is the best thing you can do to be successful.